Solitons are fascinating phenomena in both classical and quantum systems, representing stable, self-reinforcing waveforms that persist over time without dissipating. These solutions often emerge in nonlinear systems, where complex interactions between elements defy straightforward cause-effect chains, instead producing enduring configurations. One of the most compelling examples of solitons arises in Quantum Chromodynamics, QCD, the theory describing the strong interactions that govern the behavior of quarks and gluons. In QCD, solitons appear in the form of skyrmions and flux tubes, offering profound insights into how complex, stable structures can emerge from dynamic fields. The persistence and stability of solitons map intriguingly onto the concept of triadic homeostasis as described in systems theory. Triadic homeostasis refers to the balance between three interdependent elements, where each part sustains the others, leading to an equilibrium that resists disruption. In QCD, this triadic structure is exemplified by the interactions between the three color charges, red, green, and blue, carried by quarks. These color charges form a homeostatic triad, bound together by the exchange of gluons, which ensures that quarks are confined within composite particles, like protons and neutrons. This analysis will explore how solitons in QCD, particularly through the lens of color confinement and topological stability, can be understood as manifestations of triadic homeostasis. We will draw connections between the solitonic structures in QCD and the 1A coexistence and 1N equilibrium triads, which are foundational in describing stable systems of interdependent elements. In doing so, we aim to demonstrate that solitons, far from being isolated nonlinear phenomena, are deeply rooted in the interrelated dynamic balances that underpin both QCD and broader systems theory. By examining solitons through the dual lenses of QCD and triadic homeostasis, we not only gain a deeper understanding of how solitons emerge and persist, but also enrich our conceptual framework for analyzing stability in complex nonlinear systems. At the heart of quantum chromodynamics, QCD, lies the principle of color confinement, where quarks, elementary particles, are perpetually bound together in color-neutral combinations. Quarks carry one of three color charges, red, green, or blue. However, unlike electric charges, these colors must combine in such a way that the resulting particle is color neutral. This dynamic reflects a deeper principle of coexistence, where individual quarks are only meaningful within their mutual relationships. In isolation, they cannot exist in a stable state, but together, their color charges balance out to form particles such as baryons, for example, protons and neutrons. This triadic interdependence between red, green, and blue quarks mirrors the structure of the coexistence triad. In this framework, each quark, A, B, C, only exists in a stable state due to its relationship with the others. A baryon, for instance, can be viewed as the physical manifestation of the triad's coexistence, where the quarks collectively sustain the particle through mutual reinforcement. This perfectly echoes QCD's color-neutral requirement. A proton, for example, is stable only because its red, green, and blue quarks are perpetually interacting in such a way that their individual color charges cancel out, leading to overall neutrality. The gluons, particles that mediate the strong force between quarks, further deepen this triadic relationship. Gluons themselves carry color charge, meaning they not only facilitate the interaction between quarks, but also interact with each other in complex feedback loops. This constant exchange of gluons between quarks prevents them from escaping their bound state, thereby maintaining the color-neutral structure. In QCD, the nonlinear nature of these gluon exchanges resembles the intricate feedback loops found in homeostatic triads. The whole system stabilizes itself through mutual interaction, making it impossible for one part of the triad to exist or function independently. This insight into quark-gluon dynamics directly relates to soliton formation. Solitons in QCD, such as skyrmions, are stable field configurations that emerge from this triadic interplay, where the system's elements naturally support each other to form a non-dispersive, self-sustaining structure. Much like the quark confinement described by the coexistence triad, solitons represent stable, enduring solutions in nonlinear fields. These structures persist precisely because they rely on a network of interdependencies, be it in the color-charge balance of quarks or the feedback-driven interactions of gluons. The concept of equilibrium is equally fundamental in explaining why quarks cannot be isolated, a key tenet of QCD. When attempting to separate quarks, the force between them grows stronger, eventually generating new quark-antiquark pairs rather than allowing any individual quark to escape. This is reflected in the equilibrium triad. Here, the removal of any element or quark disrupts the entire system, preventing stable isolation. The energy required to separate quarks increases until the system compensates by creating new particles to maintain equilibrium. This is analogous to the homeostatic principle where disturbing one element in a triad causes the system to respond, restoring balance. In QCD, this manifests through the creation of quark-antiquark pairs, ensuring that the color neutrality of the system is never compromised. This behavior of quark confinement underpins soliton formation in QCD. Just as pulling quarks apart results in the formation of new particles, disturbing a solitonic structure requires substantial energy due to its inherent stability. In fact, solitons are often topologically protected, meaning they cannot be easily transformed or broken down into simpler states without disrupting the underlying field configuration. This parallels the idea in the equilibrium triad that removing or isolating one element destabilizes the entire system. A particularly striking example of soliton-like behavior in QCD comes from the formation of flux tubes. When quarks are pulled apart, the color field between them stretches into a narrow, stable configuration known as a flux tube, which resists breaking. This is reminiscent of the self-sustaining waveforms found in solitons, where nonlinearity and feedback mechanisms stabilize the system. In the case of flux tubes, the interaction between quarks and gluons leads to a homeostatic balance that maintains the structure, even as the quarks move further apart. This is analogous to your homeostatic triads, where the interplay between elements leads to a stable system through feedback loops. In QCD, the flux tube behaves like a soliton, stable, localized, and resistant to dispersion, highlighting how the color forces in QCD can be viewed as forming a dynamic triadic homeostasis. Another key feature of solitons in QCD is their topological stability, particularly in the case of skyrmions, which are often used to model baryons like protons and neutrons. The baryon number is a conserved quantity, ensuring that baryons cannot decay into simpler particles without violating this conservation law. This conserved quantity reflects the essential nature of each element in a homeostatic triad. Just as removing any element of a triad leads to systemic instability, altering the topological properties of a soliton would disrupt its stability. In this sense, the baryon number in QCD acts much like the conserved relationships in a triad, where the presence of all elements, quarks and gluons, is required to maintain the system's stability. This connection between topological protection and triadic homeostasis further illustrates how solitons can be understood as stable field configurations that persist through the complex interactions of their constituent parts. In summary, solitons in QCD exemplify the principles of triadic homeostasis, where stable structures arise from the interplay between multiple interdependent elements. Whether in the context of color confinement, flux tubes, or topological stability, solitons persist due to the balance of forces within a nonlinear system, a balance that echoes the coexistence and equilibrium found in your 1A and 1N triads. In QCD, the relationship between quarks, gluons, and color charges forms a natural analogy to the triadic feedback loops that stabilize homeostatic systems. The nonlinear interactions between these elements, much like in solitons, produce persistent, self-sustaining configurations that resist disruption. These structures not only provide insight into the fundamental forces governing the universe, but also illustrate how deeply intertwined relationships can lead to stability in complex systems. By framing solitons within the language of triadic homeostasis, we gain a richer understanding of how such systems function, both in the quantum world of QCD and in the broader analysis of nonlinear interdependent systems. This perspective helps illuminate the profound connections between stability, feedback, and the interdependence of elements in sustaining complex, enduring structures.